Alright, hi Year 12. So I just thought to help you all with your assessment tasks. I know that a couple of you were saying you weren't sure about certain components of how DC motor works and how that relates with Lenz's law, so I thought the best way of going about it is to ensure that I do a recording of these particular slides so you can have a look back and just hopefully understand certain bits that you might have missed out on. I will try my best to use the pointer just to direct you where to look at on the slides, as I know it is a little bit difficult, but just work with me here. So in this section of slides, we're gonna quickly look at the functions of the DC motor or the components of the DC motor and how they help our DC motor work. Okay, so this is basically the stock standard view of what a motor would look like on any electric motor. So it will have in the center an iron core to increase magnetic flux, so increase flux linkage. Inside the rotor we'll have wires to help it rotate, and obviously we'll have some magnets around that to create some kind of force or to create that motor effect, so there is some interaction and cause some kind of rotation. So if we just try and break this into separate parts of an electric motor, there are a couple of bits you need to pay attention to. Obviously, there are probably additional stuff that you can look into, but I'm just going to focus on the commutator, the armature, brushes, and the stator. Okay. Just a little video for you. So if you are using the PowerPoint or the PDF, and you want another form of explanation or animation to help you out, just go onto this Learning Engineering on YouTube and it will give you some explanations as well on how DC motors would work. So the first part we're going to look at is the stator. So the stator is, or in a standard DC motor, that's where you would place the permanent magnet or the electromagnet. So this is the place where you get the electromagnetic field of your motor. As you can see in these diagrams here, the stator is actually circular, and essentially what that means is the function of a circular container is to create a radiomagnetic field. That's to ensure that the plane of our coil is always parallel to the magnetic field. Why do we want that? Because we want maximum torque, so rotational force moment at all positions. Let me show you what that actually means with two slides after this. So just a little trivia of what is a stator. It's just magnets that are fixed to the motor and they're stationary. That's why they're known as the stator. If you look at this, what I said was the radiomagnetic field. These two magnets, these two stationary magnets here, they are not radiomagnetic fields. They're just the normal bar magnets here. And the plane of the coil, I mean this flat area. So this flat area coming across like that. I wonder if I can draw something out. Laser pointer. So it's just this flat area here coming across. That's the plane of the coil. Now, what would happen is if this is the exact same view I have over here, if I drew my magnetic field, it's going directly across like this. So it's just going directly across. Ooh. Directly across like this. Okay? Our plane is at this point or the plane of the coil is parallel, but the area vector is perpendicular to the magnetic field. This is where you get maximum force on the coil, this is also where you get maximum torque on the coil. Okay, so this position allows it to get maximum torque. But let's say if the plane of the coil changed and the plane is now like this. Just give me a moment here. I'm trying to draw this with my mouse, so it's a little bit slow. So the plane of the coil looks like this, and magnetic fields are going through the plane like this. Okay? At this point here, there would be zero torque. So our coil will have zero rotational force. It will have no force either. There's no net force either way. I'll show you why that's the case in a second. But essentially, we have no rotation here, and so it's not very useful. We can't have a motor that just kind of loses its force of rotation or has zero rotation whatsoever. And that's why in most motors, you will not see people having bar magnets as the stator, because that's not the way to go. It's not very useful either. This, on the other hand, is what you'd see in most DC motors, or motors in general. Okay? So the main difference is, instead of having magnets that are rectangular blocks like we saw in the previous slide, they are semicircular poles. Okay, semicircular. And why? Because we want to create a radiomagnetic field. What that essentially means is the plane of the coil is always parallel to some magnetic field at whichever point it's rotating. So as my coil is rotating clockwise like this, let's just assume like that, it is always parallel to the magnetic field. The plane of the coil is always parallel at some point across. What that would mean is force is always maximum. So we ensure that our force is consistent, constant, and that also ensures that our torque is constant. So you don't want a motor that kind of speeds up and then slows down, speeds up and slows down. That's not very effective. That's not very reliable to use as an application in real life. So what they tend to do instead is, by having it as a radiomagnetic field, you can allow the motor to rotate at a constant force, and so far more reliable that way. As you can see here, most cases you'll see the stator position like this, and then you'll see little gaps between the magnets. You'll really see it where they connect together, and so it'll rotate. But obviously one of the questions would be, same question as I asked before, is what if the plane of the coil went down through this area like so? If it went down like that, there's no magnetic fields up here, there's no magnetic fields down here. So our coil doesn't have any force of rotation, it doesn't have any torque. But as we know, it still turns. Why would that be the case? Now, remember, there are in physics universal laws like conservation of energy, conservation of momentum. Okay, we know that in terms of Newton's law of inertia and conservation of momentum, the coil was rotating up till this point here. Up till that point, it was still rotating, which means, because of the law of inertia, because of conservation of momentum, our coil will continue to rotate even though there's no torque added onto it until it reaches the south pole magnet on this side, and then it starts again and builds up again. Okay, torque will go 0 again down here. Ooh. Sorry, that was our lovely school bell there. So it goes down through here, and again, torque is 0 down here. Okay, but because of inertia, it'll continue to rotate along, and that's essentially what our radial magnetic field does. Keeps the torque constant and continuously rotating. Next we have is the commutator. Just give me 1 second to correct one thing. Okay, so I just quickly changed a note on one particular point. So the commutator essentially passes any electricity from a power source. So if we were in the lab, it would be the power pack. It goes through these brushes into the commutator and then into the coil. Once the current goes into the coil, it will interact with the stator, the magnetic field's there, and then a force will be applied, as you can see from these diagrams here, and it will start rotating. Now, because we're talking about a DC commutator or DC motor, this is where AC and DC really differ, okay? In a DC commutator, they use a split-ring commutator. AC, they use a thing called slip-ring, which I'll go through a little bit more when we go to that topic. But essentially, a split-ring commutator will automatically change the direction of the current in that particular wire at every half rotations. Okay? Why do we do that? Again, we want to ensure that the torque is consistent and our motor is consistently going or rotating in the same direction. So in this case here, if I just show it, our motor looks to be rotating clockwise. Okay? And it's going clockwise here. How do I know that? Cross into the page, so use your right hand rule, put your thumb into the page. B is pointing to the left, so the finger's pointing towards the left. F is the force, so your palm is facing upwards. As you can see, it pushes up. If I look at this side here, F is down, so clockwise that way. Okay? What you will find is between B, C, D, if we just track the same wire, it does a little interesting thing where the current reverses on itself. Okay, and we'll go into a bit more explanation why that's the case, or what's the purpose of doing something like that. Okay, so this is our split ring commutator. I've just tried to highlight where they are. So this initial one is colored in blue. It's connected to the negative terminal. And this one over here is colored in black, and it's connected to the positive terminal here. And so let's just allow it to rotate. It goes rotating clockwise. It goes here, and then here, and then here. So that. Now something really interesting happens here. This blue commutator has now in C disconnected with the negative terminal. The black commutator here has disconnected from the positive brush and now connected to the negative brush. And if I look at it here, it looks like this. LK is the while. It was initially coming out, going in. MN, same idea. The current was initially going into the page, out the page. So the current in those wires have essentially reversed after half a rotation. So the idea is very simple. if I continue on using my right hand rule for scenario C, LK is coming or going into the page, so it's going into the page. The magnetic field in this example is going to the right hand side, okay? So my palm is pushing down, it's going down. By having LK reverse the direction of its current, I've essentially allowed the motor to continue the direction of rotation. So to continue on its same directional rotation. If LK, instead of coming into the page or going into the page, is still coming out the page, so my thumb is still pointing out, okay, follow me here. Thumb is pointing out on LK because the current is coming out the page. B is still going to the right. F, my palm is now pointing upwards instead of down, so LK, if it was a dot, and I'll try and draw it out here, so instead it's a dot, it goes up this way, and MN, if it was still going into the page, okay, it will point down. Can we see a problem? Our motor would rotate in the opposite direction. Now initially we have it rotating clockwise. If the current did not change every half rotation, it's now going to rotate backwards. And we can't have a motor that rotates backwards because that's not really convenient, right? You can't have a windmill that's suddenly, or you can't have a fan on a hot summer's day reversing on itself every half rotation. You won't get any cool air coming through, right? So that's the function of a split ring commutator on a DC motor. It's to reverse that current and also maintain the same direction of rotation for our motor. Okay? The other thing you'll see is I also mentioned that where the plane of the coil, this bit here, is perpendicular to the direction of our magnetic field, the force is 0, or the force is 0, rotation is 0. Why is that the case? Have a look. Now, according to Newton's, or according to just looking at the net forces, they're pretty much in the same direction. So, well, not direction, sorry. They are the same magnitude, so it has the same magnitude, but they're in directly opposite directions to each other. Not quite the same as when they were over here, because that unbalance in net forces allows it to rotate. This, on the other hand, the net forces are directly above and below each other in the same magnitude but in opposite directions. So they effectively cancel each other out. That's why there is no force of rotation when the plane of the coil is perpendicular to the magnetic field. Not because there's not because the force is exactly gone, but they've cancelled each other out on both sides. Okay? And that's why it won't really work. For the motor, at least. Alright, so just a little summary of what the function of a split ring commutator is. It's just the mechanical switch that automatically changes the direction of the current flowing through the coil when torque becomes 0. And remember, the reason why the coil continues to rotate when torque does become 0, inertia and conservation of momentum. This is just a little summary that we used in class and we talked about. Have a read through it, see if there's anything you want to ask about. If there isn't anything to ask about, then all good as well. So give yourself maybe a minute or so to read through that, and then just move on to the next part. So next one we have is the armature, or armature, some people call it. Essentially, this is where you put the loops of coils, so where you want to do your number of turns of coil, copper wire, this is where it is. Usually the wires are wrapped around a ferromagnetic core, so some kind of iron core here. As you can see in this picture down here, there's a little couple of cuts down here, so a little bit of cuts. That is the lamination that's happening. Remember, that's to reduce the amount of eddy current, which we'll talk a little bit about more down there. And essentially, we're trying to transmit the current, interacts with the magnetic field to generate torque and rotate the motor. So we need current going through these wires, and it needs to interact with the magnet of the stator. That will cause the motor to rotate because of what we talked about with the motor effect. The next bit is the strong magnetic field. So how can we increase the field strength of what we have? You can increase the number of coils. So number of coils on the soft iron core. That can intensify the magnetic field there. You can also ensure that the magnetic fields are transferred more efficiently from the permanent magnets to the armature coils than having air core in the armature. So having magnets there would also ensure that better transfer, or just using electromagnets. So ensuring that we have electromagnets, that would also help strengthen our torque, essentially. Next bit is the brushes. Okay, so the feature here with the brushes is they're not actually connected to the commutator, so they're just barely touching. Okay, they're not actually fixed onto the commutator, so they're not rotating when the commutator is rotating. The commutator essentially brushes past, hence kind of the name. So when the commutator is rotating, it essentially makes contact, so it just touches the brushes and it will just rotate around. Okay, so obviously you need some kind of conducting material. They use graphite for brushes, and they essentially connect the DC source from the power pack to the commutator. The only problem with using brushes is every time it connects and disconnects, as you would know, if there's a high enough potential difference between the commutator and the brushes, you can cause sparking, and that can damage your motor over time, and that's not very convenient. The next part we have is also rotating split-ring commutator and the circuit. Yep. And the other point of having brushes is to ensure that our coils don't ever get tangled when rotating. So if you imagine, and what we mean by cores is the cores that connect to the battery here. If these brushes were rotating with the commutator, eventually these wires on both sides will end up spinning on each other and tangling up on each other. That's not what we want. By having this being disconnected to the commutator and allowing the commutator to just rotate around upon itself, this will ensure these cores don't ever overlap and tangle, and so you ensure that the circuit doesn't have to unwire itself after each time. So that's pretty much what the brushes do. If we look at a simple DC motor, Direct current has this interesting thing where there's a maximum part of how much torque you can generate. So like I said, when the plane of the coil is parallel to the magnetic field coming across, and then it will be 0 when the magnetic fields just go through the plane of the coil like that. Okay? So torque isn't consistent for a DC motor, so it's not very practical. So a way that they counter that is by doing this. Okay? So this kind of looks weird to you here, but instead of having one coil rotating around here, what they actually do is they'll also have another coil at a different angle. So maybe I'll use a different color. We'll have another coil that is here. Well, that's very awkward looking, but either way. And then we have another coil here. And then I'll redraw it here, here, and here. So if I have an additional coil that is 90 degrees of my original coil, what I get is when one coil is at its minimum, the other coil is at its maximum. Whoa, missed out there. So like this. So when one coil position is at its minimum, the other coil is at its maximum torque. And so we get something like this, a resultant torque like this. So based on that, we might have some deviation in the amount of torque we generate still, but we won't have a point where it's completely 0. And that can be very useful too. Okay, so just a summary. If I want to increase the torque, so the rotation force on a DC motor, what do? Increase the force on both sides, increase the width of the coil, so that's increasing the area. We will go into the formula for torque. Use more than one coil mounted on the armature, what I said just then. If I want to increase the force, increase the current on the coil, increase the number of loops of wire, stronger magnetic field, and use a soft iron core. Remember, the soft iron core is to increase magnetic flux linkage, and that should increase the amount of force on there. This concludes the lesson on DC motors and its components. The next stop, we're going to be talking about what the effects of back EMF has on the motors itself.